Hi, and welcome to this look at some applied enthalpy of reaction questions in aqueous solution. We're going to take particular attention to the consideration of the effect of change in total volume of solution on the energy that's released or taken in. So I've taken the question set and split them up into several slides. So questions A and B we'll do first. So they want us to construct a balanced equation for the reaction between zinc and copper 2 sulfate. That's straightforward enough. It's a simple displacement like that. And then it says, when the two are mixed together, would you expect the temperature to rise or fall? And the reason for this. So looking at the enthalpy change for the reaction, it's negative. So this should mean the temperature should rise because it's an exothermic reaction. And it's evident from the negative sign of the value of the enthalpy change that we can make that conclusion. So in this part of the question, they tell you that 50 centimeters cubed of a 1.0 moles per decimeter cubed solution of copper 2 sulfate is reacted with an excess of zinc powder. So calculating N, the moles of copper 2 sulfate, you do N equals C times V. And that gives you 0.05 moles. They want us to calculate Q, the expected energy change in this reaction. So, if you go back to the earlier part of the question, where it was minus 219 kilojoules per mole, this is 0.05 moles, so you just multiply the two together, and that gives you minus 10.95 kilojoules. Now, I'm saying minus 10.95 because it's energy being released, because it's an exothermic reaction like we saw before. Then it says to rearrange Q equals mc delta T to give delta T. And then, given that C equals 4.18 joules, not kilojoules, joules per Kelvin per gram, calculate the maximum expected temperature rise for this reaction. So what we've really got to do is take this value and multiply it by 1,000 to make it joules instead of kilojoules. So that allows us to end up with 52.39 Kelvin, or 52.39 degrees C. It doesn't really matter which way round you write that. So the next part of the question is calculate the maximum expected temperature rise if the experiment is repeated with these two different arrangements. So you need to look at the volume and the concentration. So let's have a look. If we take the first one, what's happening is you have the same volume but half the concentration. So half the moles reacting, so half the total energy is dispersed into the same volume. So you therefore get half the temperature rise. So that's 26.2 this time. So in the second scenario, what's happening is you have twice the volume but half the concentration, meaning the same moles as the original reaction. So the same energy is released, but it's dispersed in twice the volume of the solution. So this reduces the temperature rise because the energy is more spread out. So again, for a different reason, half the temperature rise occurs, 26.2 degrees C. Now we've got to think about it. They want you to list the factors that determine the temperature change during a reaction. So firstly, it's the enthalpy change of the reaction, whether it's exothermic or endothermic. That'll give you either a temperature rise or a temperature fall. Then, the total volume of solution the reaction is occurring in. This affects the size of M. M is the mass of water being warmed or cooled in Q equals mc delta T. And finally, the concentration of the reactants in aqueous solution. This will affect the moles reacting and therefore the total energy released in the reaction. Okay, hopefully this has been a useful look at a rather applied aspect of Q equals mc delta T. As always, thanks for listening. Until next time, see you soon.